Hello everyone for our machine design lab uh, pressure. Our topic is actually design of a biogas cylinder for rural households. So for that designing process, we have gathered our data, uh, which is our last step is which is optimization actually. For that we have done another calculation. So our height is similar. We have got above 179 millimeter. Our diameter, outer diameter 360 millimeter. Our previous wall thickness was 1.5. So for now we have got a previous thickness of 3 to 3.5, and with stiffeners means we can, uh, if this is our cylindrical biogas cylinder or pressure vessel, what we can say, this height is actually 179 millimeter, and this is 90 millimeter, and this radius is 180, and this diameter is actually 360 millimeter. And in previous analysis we have used 1.5 millimeter thickness, and now we'll use the maximum thickness, which is 3.5. By calculation we have found that 3.4 will be a for safer thickness value. Here we can see that global member stress, from here we have got the safety factor 4, which is our desired on safe globally, but locally this is unsafe. Globally safe means the stress we are getting, the equivalent stress we are getting is around 52. This is actually the global value. So by dividing, actually 59.75, so whatever, this is around in 50 to 60 range. So this is the global value. So for this the factor of safety is 4, which is high. And if we see local means there in the joint ends, their local stress is concentrating, so there is safety factor, their safety factor is low. So for this we will increase our thickness value. So let's design the cylindrical pressure vessel with ellipsoidal ends in SolidWorks 2009. So for this we have selected front plane, and then we will simply use center lines. Okay, nice. Then again center line, and we will draw lines. So like this, the radius is actually what I have said before, 180 millimeter, and there will be another line. So this is the cylindrical part, so you will understand slowly, gradually. So for this we will use this as midpoint. For the line will divided into equal parts. So the dimension here will be 179 millimeter, as we have mentioned. We got these dimensions from our hand calculations. So we will show if we have time in our hand. So we can now take another lines like this. Okay, this is 180, and this one is also 180. Nice. So these will be, there will be two lines. Okay, and there will be another one. Okay, so we are deleting those, and we are fixing it. We are fixing the points. The point should be fixed. Okay, the point should be fixed. Okay, and this one should be fixed also. The point should be fixed. 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 we should put the dimension. Sorry. First of all, actually we should put the dimension. So there will be two lines. There are two lines. So smart dimension option. It will be 90 millimeter. It will be 90 millimeter. So after that we will cut those lines. Okay, good. Then we will fix these options, lines. Okay, and we'll fix these two. Fix. Then this one is also fixed. We are fixing this because it will move. If we put another point here, it will move. So we shouldn't move those lines or points as we are designing some critical things, which is actually pressure vessel. It can burst anytime, anywhere if the pressure exceeding the stress value, when the stresses are higher actually. So we will now select tangent arc, not tangent 3-point arc. So from here we will draw something like this. We can put the angle 52. So for this the value is 299.53 radius, and from there the tangent arc, not the tangent, 3-point arc, the value, this one must be the same. Okay, so this one also 52, 299.53 radius. So we have draw our vessel, pressure vessel sketch. We have draw our pressure vessel sketch. So we'll delete these fixing points. Okay, and is there anything? Yes. So we have deleted those things and we have got the structure. So we will revolve this sketch. For before revolve, we will use offset entities, and we will put our desired thickness value, which we are assuming for this time 3.5, and we will use fillet radius around 8 millimeter. Okay, so here we'll use 3.5. okay, and there we will fix this point, and we will fix this too. This we will fix this also. Okay, so we will now align it to meet coincident. So this can be maybe coincident, as this is fixed. This can be coincident, so we are not fixing things. So this is fixed, so we can use this as coincident. So this is coincident. Okay, and this one is also fixed, so you can use coincident. Okay, so all right, so for revolving this structure or sketch, we will close this using lines, and we will also close this using lines. Okay, nice. So now we'll use revolve feature. So you can see it is revolving. We are getting a cylindrical pressure vessel, so that's great. Okay, so this is our pressure vessel, our things. So this is fixed actually, so this is okay for now. There is showing some alert. The case is over defined actually, considering uh, some definition or okay, this is over defined, so we can close the this customize. If this is over defined, we have maybe fixed something. This we can so this is coincident. Okay, that's not a big deal if this is over defined. The thing is, we need to analyze this in ANSYS. Okay, so we can revolve this, no issue. Okay, so for now we are closing this. It is okay now, so we'll use here fillet with a radius of 8 millimeter. Okay, so we have, so is this hollow? Yes, this is a hollow shaped cylinder. So we will draw the support now. For this we'll use 156.5. Let's draw the support in this plane. So we'll use a circle with the radius of 100, and we will again offset the circle with 3.5 millimeter offset value, and we'll use now extruded boss base command. From here everything is okay, so the direction will be negative downwards, and we can take this as 45 millimeter. That's not an issue. So hiding the plane. So this is our cylinder, so that's it. This is our cylinder. So now what we'll do, now we'll slice this cylinder for better analyzing the stress. Okay, so for this again one thing, from here we can choose material. And from our analysis we are using aluminum 6061T6. We can choose here. From there, if we choose it, apply. After applying, we can evaluate mass properties, this cylinder weight, then volume, etc. we can measure from this process. So for now I am not doing this. For now we'll slice the cylinder into some part. Like this is cylinder, mainly this will be symmetrical in any. If we cut like this, it will also be symmetrical. If you cut like this, it will also be symmetrical. So we'll cut a little portion of the cylinder like a cake, a birthday cake. So let's do that. For this process, we'll select top plane, then top plane, then what we'll do is top plane sketch, then we'll select top plane. What we can do, we can put two lines here, then again we'll slice it like a cake. So this can be like this. Okay, great. And we will now use tangenter to fill this area. So okay, here, then again tangenter, select this point and stop in this radius. Okay, then again use escape to cut ESC from the Windows keyboard, select this and stop here, and again escape button press for cut, then again select this, then stop here. So we'll now extrude cut use, then through all both, then okay. So here we have cutted our cylindrical part. So for that cut, before that cut, we will save our file. So we will save our file like 3.5 mm thickness. So our cylinder is 3.5, right? So we will check what is the thin wall assumption range. We'll check this is thin or thick. So a thickness diameter ratio less than 110 or 115, or a radius thickness ratio greater than 10. Greater than 10 radius thickness ratio is thin wall. So our radius is 180 and thickness is now 3.5, so our value is 51.42. so we are assuming thin wall assumption. Okay, so we'll save our file and then we'll extrude cut through wall both. Okay, and we'll use parametric view. So isometric. Okay, that's not an issue. Then we'll choose file, then again save as. So now we'll save our file as parasolid format, then okay. So we'll now analyze this cylinder in ANSYS 2022. So for this we will choose static structural. We'll put our material data, which is aluminum 6061, Al6061, and isotropic electricity, and our EOS mole gas is 6.9 E10 Pascal, and our Poisson's ratio is 0.33, and we are using ELSN value as what? As 240 megapascal. So select megapascal from here and this will be 240. So we can now change it to pascal. That's not an issue. if we change that to Pascal or megapascal. So we'll open design modeler. After that we will open our desired geometry. So this is interesting, the thing. FEA, verification, validation, the things are actually interesting. So we'll first axis, choose import geometry, our PC drive D, our file type all files, desktop, this PC, D drive, this is actually XT format file. We'll open it and we'll click generate. So let's try to open. Import external geometry 3.5, open, giant. So this is our pressure vessel. We have got the portion, the symmetrical portion. So now we'll analyze this. We'll open model. So let's try what happened. Let's try open model. This is going to be very interesting, very interesting. So we will analyze this. Okay, so for geometry there, maybe this is not merged. This is saying a separate geometry. This is not a separate geometry. Oh man, we have got a problem in our geometry. So let's change that first. So we'll delete cut extrude. So we have deleted cut extrude. Okay, so we'll delete this feature, boss extrude, and we'll again draw this. Okay, so we'll take plane. Our plane is here. You can hide the sketch. We'll take this plane, and from here what we'll do, we'll select this and we'll click on sketch. Then we'll put 100. So before doing this, we'll delete it. Before doing this, we'll fix the plane. Okay, we'll fix the plane. We'll fix the plane first. So we can delete the plane. Okay, you can choose another plane. Feature reference geometry plane, flip. We can choose 155 155.6 or directly 155. Okay, then we can draw a circle here again with a radius of 100 millimeter, and using offset entity we'll now use extrude ball space. We'll use merge here, tick mark, and 45. So this is nice. So but we can also use fillet here. So let's see what is. So the joint is very much lower here, so we should put another, we should put the plane up, should put the plane very up. So we'll edit the plane. We can choose 153 millimeter, 152 millimeter I think. Let's try from this, then sketch. Plane, sketch. The radius will be 100 and offset entity. Okay, the feature we will use extrude boss base feature, and blind, this the direction will be reverse, so the plane height, the plane, so the cuts are showing here. We should not show the cut here. I think this won't be a issue, but for this we can fix again. This is actually something trial and error process, you know. So again we can delete these things. We can choose plane edit, and this can be 153, I think 153. Okay, so close. Okay, select the plane, then sketch circle, 100 millimeter circle radius, offset entity. Okay, then extrude boss base, direction reverse. Okay, then we'll see what the condition. So now this is very okay, very okay. Okay, so we can now cut the cylindrical portion. We can cut. We'll choose top plane, then again the same thing, we'll use something like this. We'll use something like this, and now we'll use the tangent arc again. So this, from here, this, from here, this, from here tangent arc, this. Okay, and from here tangent arc, this. So we'll cut it using extrude cut command. Cut extrude through all both, then we'll put simply okay. So we have cutted our cylindrical shape, and we can use isometric view, then file, save as. So we'll select uh, parasolid format. Okay, override. So now we'll pin the geometry, reset. Okay, we'll pin the model. Okay, and we'll open design model. So we are doing things very slowly. Export geometry, this. Okay, then simply generate. You can cut the window. The geometry is saved, already saved under the geometry panel. So from here we'll now analyze the model. So let's analyze the model for 3.5 millimeter thickness. So first of all, we'll update the geometry of solid from here, assignment. So you can see the body is totally marched now and there is no part here. So this is very interesting. The things are very interesting. We'll use aluminum 606 on, then we'll use the symmetrical solution from here, and we'll open a cylindrical coordinate system. Cylindrical. So we'll choose cylindrical, and for this we will use X rotate 90. So for cylindrical coordinate, we know this is actually we have set up the cylindrical coordinate. So for this, if you have the basic theory of cylindrical knowledge of basic theory of cylindrical coordinate system, you can relate this. The y-axis will rotate and x and z axis is like this. So from here we will select this geometry, apply, nice, and the geometry selection is default. So we can use now symmetry, cyclic region. The lower boundary will be this one, not like this, the overall face. Okay, the higher boundary will be another face. Okay, and this will be cylindrical coordinate system. So isometric view is like this. So okay, we can fix the view from by pressing the mouse scroll button. So now we'll update the mesh for element size 2 millimeter, and we will use fine mesh, and we'll use smoothing high. So we'll update the mesh. So our mesh is, we have updated our mesh. We can now use, I think we can use a very good finer mesh in the joints. I think we can use sizing in the joint. Sorry, not sizing. Refinement in the joints, corner edges, this edge and this edge. Okay, so the refinement actually not possible here, so we can delete it. So let's run in 1.5 millimeter element size, get. Okay, we have generated a very good mesh, no worries. So let's put it here, static structural insert, pressure. From here select these three faces, use pressure 0.5 megapascal, which is around 5 bar, and for fixed support we'll use fix this support face. Okay, so apply. Okay, so from solution we'll took the stress equivalent bond misses, then we'll use toolbox stress tool safety factor. So we'll run the solution. So let's do something theory. So here our max yield resistance is 240 megapascal. So if we get the von Mises value less than this value in megapascal, in critical or local or overall region, so we can say this is safe design. So yes, right, our stress is now 110.29 maximum. So if we use probe from here, the stresses are very low here, 24 20.94. so actually this is matching with our updated hand calculation, I think. So our updated hand calculation, let's take a probe first here. So 20, around 25. So let's look. So here is our longitudinal stress is 29.9, and hoop stress is 59.7, around 60, around 29. So this is very close to our value, and we can update the calculation if there is an error, but our analysis is okay for now. So our analysis is okay for now for 3.5 millimeter thickness. For 3.5 millimeter thickness, so this is the critical region. And if we use graphs, from here, what can be the graph actually? There is skewness graph. So let's find the skewness graph. So mesh metric skewness. So see the skewness graph. Control, let me take it 50 update. Okay, so what we are seeing actually, so where is this? So select mesh, and this is our graph. So this is our mesh metric graph. we can see that the maximum uh, zone is around 0 point around 0 to 0.8 0.8 or 0 point, we can say 0.8 actually. So this is the bigger skewness is actually in 0.25 0.3 in this region. So our skewness is okay. So if we use this, our stress rule, our safety factor is 0 to 15. So from here we can, if you use prop, our safety factor is 9 10, we have increased our safety factor. So okay, so I think we can use, we do not need this much higher safety factor. So I think we can use uh, around 2.5 millimeter thickness around. So this is actually a safe design. So that's all for today. Thank you everyone.